Hi, this is Sheikh Abdullah from Allah Technologies. We are training partner for Nuvoton. In this video demo, we are going to see the feature of Gpio in NuMicro NUC140 devices from Nuvoton. It is ARM Cortex M0 based microcontrollers. Gpio overview. It has up to 80 Gpio pins. It can be shared with other function pins depend on the chip configurations or control register configurations. These 80 pins are arranged into 5 ports, namely GPIO A. It has 16 pins. GPIO B. It has 16 pins. GPIO C, GPIO D, and GPIO E. All the ports equipped with 16 pins. For each ports, we are having separate control register to configure. Each one of the 8 pin is independent. So you can configure the IO mode for each pin individually using the register called GPIOX_PMD. X stand for port name, maybe A, B, C, D or E. It is a 32-bit register to configure the IO type of each IO pins belongs to that particular port number. Say for example, GPIO A_PMD means that is a control register to configure the IO pins of GPIO A. And GPIO B_BMD is a control register to configure the IO pins of GPIO B and so on. Now we will see the features of GPIO on NuMicro NUC140 devices. It has 4 IO modes, namely quasi-bidirectional, push-pull output, open drain output, input only with high impedance. So it has 4 IO modes. And support TTL or schemic trigger input. Okay, user can select based on the input voltage standard. This IO pin can be configured as interrupt source with edge or level setting. Okay, so we can trigger a input interrupt either on edge or level. User can have option to select, and these are maskable interrupt. Again, if you want GPIO based interrupt, you can unmask it. If you don't want interrupt source or GPIO interrupt source, you can mask it. Now we will see the IO mode in detail. So if you want to configure the IO mode as input mode, the value for GPIO X_PMD N for that particular 2-bit. Okay, each it's a 32-bit register. Each 2-bit represent 1 pins. So say for example, GPIO A underscore PMD means it is a control register for GPIO port A. So it is a 32-bit register. Bit location 0 and 1. Okay, these two bit going to define the IO type of pin number 1 of GPIO port A, and bit location 2 and 3 is going to define the IO type of GPIO port A, and so on. Okay, so the particular 2 bits, so I'm talking about 2 bits. The 2 bits are very 2 bits are common actually for all the IO types, for the all the IO for the all the IOs. Okay, um, if the PMD GPIO X underscore PMD register value is equal to 00, means this IO pin is in tri-state. It's configured in tri-state without output drive capability. This mode is useful when if you want to interface voltage source. Okay, the loss of voltage is very less. It's like a no load significant can achieve. It won't load the source. And GPIO X underscore pin control register values reflect the status of the corresponding port pins. Okay. If you set the control register GPIO X underscore PMD is equal to 0, 1, then the IO pin support digital output function with source or sync current capability. Okay, the bit value in the corresponding bits of GPIOX Dout control register is driven on the pin. If it is a low means it will drive low, it is a high means it will drive high. Our next IO mode is open drain mode. If you want to configure this IO type, you have to configure the GPIO X underscore M PMD control register is equal to 10. Okay. Once if you configure this value, the digital output function of the IO pin support only sync current capability, and an additional pull-up resistor is needed for driving high state or driving high. The bit value in the corresponding bits of the GPIO X and underscore Dout control register is 0. Okay, the value of the control register GPIO X underscore Dout is 0. The corresponding pins drive low output. The bit value of GPIO X Dout control register is 1. The pin output drive high, that is controlled by external pull-up resistor. Our next IO mode is quasi bidirectional mode. The GPIO X underscore PMD is equal to 1, 1. Then the IO pin supports digital output as well as input function at the same time. So quasi bidirectional mode. The GPIO X Dout control register is 0. The pin drive a low output on that corresponding pin. If the bit value in the corresponding bit of GPIO X Dout register is 1, then the pin will check the pin value. The value is high, there is no action required. The value is low, then the pin will drive strong high with 2 clock cycle on the pin, and then disable the strong output, and then the pin status is controlled by internal pull-up resistor. So programmer has to keep in mind, after reset, the IO type of all pins stays in quasi bidirectional mode, and port data register GPIO X means it will common for all ports A, B, C, D and E. DO control register reset to 0xFFF, sorry, 4F. So once if you start writing a code, if you want to configure the GPIO, user has to use control register. They have to configure the control registers, which mode they want, or the value they want to drive, or what's the value, if they want to read the value, what kind of register they have to access. User have to write the program, user have to aware of all the control register before programming the GPIO. Okay, that is the one method. And another method is using Nuvoton's driver file. Okay, once if we add that Nuvoton provided DRV GPIO driver file, you can access the functions, GPIO functions. No need to access the, no need to configure the control register. Okay, you can directly use the functions available to configure the GPIO. This method is very easy to write a code. Okay, here we are having here have four common GPIO function called. First one is drv GPIO underscore open. It is a function to set the IO type. It has three arguments. One is IO group. Okay, we have to select one of the IO group. It may be GPIO A, B, C, D, or E. Say for example, if you want to configure port B, means for that the argument is E underscore GPB. E means enable GPIO, B means port B. And next argument is port or pin number. It starts from 0 to 15. Each group has 16 pins. So if you select the IO groups, we have to select which pin you have to configure in the particular IO groups. Okay. Next is IO modes. As we saw earlier, each IO pin support 4 IO type. That IO mode we have to select. We have 4 IO modes. To configure the pin as a output mode, the argument is E underscore IO underscore input. If you configure that particular pin as a output mode, the argument is E underscore IO underscore output. If you configure the pin as a open drain IO mode, the argument is E underscore IO underscore open drain. If you configure the IO, if you configure the pin as a quasi bidirectional mode, the argument is E underscore IO underscore quasi. Next function is drv GPIO underscore set bit. This function is used to drive high at the particular pin. It has two arguments. One is that IO group, one of the 5 groups, E underscore GPA to enable the GPIO port A, E underscore GPB to enable the GPIO port B, E underscore GPC to enable the GPIO port C, E underscore GPD to enable the GPIO port D, and GPE to enable the GPIO port E, and next is port number 0 to 15. And next function is drv GPIO underscore clear bit. This function is used to drive low. It has two arguments. One is that IO groups, one of the 5 groups, and port number 0 to 15. Once if you configure that IO type as an input, then to read the value we have to use the function called drv GPIO underscore get bit. This function is to read the GPIO pin to input. It has two arguments. One is the IO type and port number 0 to 15. Before going into the demo, you will see that new LB NUC140, that is a NUC140 based learning board details. This is a NUC140 based learning board. Here's a device, NUC140 target device is there. This board we are having a lot of onboard peripherals like 128 cross 64 dot matrix LCD panel, 4 onboard LCD onboard LED, 1 RGB LED, 3 cross 3 key matrix, power pins, reset button, user inputs, variable resistor, GPIO pins, buzzer, codec, line in and line out, USB device. This device is powered by 5 volt DC power supply, UART for communication, CAN and LED interface, 4 7 segment LEDs. Okay, the communication between PC and the target device is through ICE bridge NULink debugger. Okay, we have to connect a USB from PC to this board to make the communications via this debugger. To know about target device pin details, that is interface to onboard peripherals, please refer uh, learning board user guide. Okay, the learning board user guide, you can see this pin pin column, function column, and block column. These are the pin of a target device. Okay, these are the pins are interface to that onboard peripherals. Say for example, um, buzzer is connected to general purpose IO port B 11th pin. If you want to interface CAN, you have to configure this pin, function pin. Okay. To know about the pin definition, please refer learning board user guide. Now we will see the demo of interfacing onboard LED with GPIO pins. This is Scale Microvision 4 software development environment tool provided by ARM. Okay, here I already opened that project. Under the project, we are having 3 subfolders. These 3 subfolders are very common for all type of applications. First one is CMSIS, Cortex M0 software interfaces standard files. These files are provided by ARM for the processor. It includes platform independent abstraction layer. Next is a source file. Here we have to include our application code. Next one is library file. Okay, based on that functions what we are using in our code, we have to include that appropriate peripheral specific library file. Now I am opening this application code by double click. Yeah, it's our code. Here the project is to interface GPIO pin. The pin name means GPC12 to control the onboard red LED. Okay, to control we have to provide low active output. That means to turn on that onboard red LED, we have to drive low signal at GPC12 port. Okay, GPC12 means it's the 12th pin of GPIO port C. Here we included device specific header file and we included peripheral specific header file. Okay, these header files allow us to use a function specific to the peripherals what we are using in our code. It's the main code. First step of the main code is we have to configure the system clock. I want to set the system clock to run at 48 MHz. So I am using the function called drv sys_open. Okay, that argument we have to provide the clock frequency. For 48 MHz, here I am writing 48 followed by 6 zeros, 48 MHz. You can see here the function called unlock reg and lock reg. Okay, why we use this function means system control registers, some of the system control registers are write protected. Okay, to disable the write protection we use a function called unlock reg. Okay, and to enable or to re-enable the write protection we are using the function called lock reg. This function available in the library file called drv_sys.c. And next is a user defined function called init_led. This is a function to initialize the onboard LED. That initialize means we have to configure the particular GPIO as output because LED is an output device, and we have to turn off the LED. Okay, these two process comes under initializing. So come to that user defined function. First function is drv Gpio_open. Okay, this function is to set the IO mode for a particular pin. This function has three arguments. First one is IO group. We have to select that particular IO group. Here we have to configure GPIO port C. So I'm enabling that GPIO C by providing the argument called e_gpc. And next is the pin number or port number. So here is 12. And next argument is output type or IO type. Here I want to configure the 12th pin of GPIO C as output. So the argument to configure the particular pin as the output is e_IO_output. Okay, here we set GPC12 pin to output mode. And next function, the drv Gpio_set bit. Okay, we have to turn off the LED because of active low. We have to drive high at GPC12 pin to turn off the LED. So I'm using the function called set bit. Okay, this function has two arguments. One is that IO group and port or pin number. Here IO group is GPIO port C. So the argument is e_gpc and port number is 12. These two functions are available in the library file called drv Gpio. Now we initialize the LED, onboard LED. Next is a condition loop. So while loop, while of 1. While of 1 means this condition is always true. So this condition is going to execute forever. So it's a kind of infinite loop. Okay. So first statement in this loop is a function. So drv Gpio_clear bit. Okay, clear bit means This function will drive low at the particular pin. So uh, because of active low, if you drive low at the GPIO 12, it will turn on that LED. So this function has two arguments. One is the IO group and port number. Here IO group to turn on the GPIO C is E underscore GPC and port or pin number is 12. This statement or this function will turn on the LED. Next, it's a delay function. So drv sys underscore delay is the number. If you want to change the delay time, you can change this number. You can change the number to if you want to change the delay. Next is we are turning off the LED using that set bit function. Again, we are giving same delay. So this statement what it will do this load. Okay, first it will turn on the LED. Second is it will wait for some delay. Next it will turn off the LED, wait for same delay. Again it will turn on, wait for some delay, turn off, wait for some delay. Okay, nothing but it will blink the LED, onboard LED. So now we have to create a output file or executable file. To create that one, we have to build this project. Here you can select this icon to build this project. It will invoke compiler, assembler, linker, okay, to create an output file. Here you can see there is no warning or there is no error. Okay, now we can going to download the output file into that board, target board. So to load, here you can see the icon called load. Okay, so here it's showing that description as download code to flash memory. If you click this one, now it's download. Okay, you can see the output, the board.
We are going to see the demo of interfacing onboard LED to the GPIO pin. So the output files are already loaded into the on-chip flash memory of controller. To execute the code, I'm resetting the controller. You can see the LED one is blinking.
Now we will see the demo of interfacing 4 onboard LED to the GPIO pins. Hi. In this demo, we are going to use LED macros to control 4 onboard LEDs. This is a project name GPIO underscore LED 4. It has 3 subfolder. So I told in a previous previous demo, these 3 files are common for all type of applications. Okay, here the files are same under the CMSIS file subfolder. Library files also same because we are going to configure system control registers and GPIO peripheral control registers. And the source file is only going to differ. Okay, here using macros to control 4 LEDs. That LED 1 is connected to GPC 12th pin and LED 2 is connected to GPC 13th pin. LED 3 is connected to GPC 14th pin and LED 4 is connected to GPC 14th pin, 15th pin. Again, all the LEDs are low active output to control. The device specific header file and peripheral specific header files we included, and we are defining the macros. Okay, to initialize LED 0. Okay, LED 0 is connected to pin number 12th of GPIO C. Okay, To defining that particular pin as a output, we are defining that particular pin IO type. We have to use the function called grv gpio underscore open. It has three arguments. One is that IO group, port or pin number, and IO type. IO group is GPIO port C. So that argument is E underscore GPC, and port number for LED 1 or LED 0. Okay, this example LED 0 is connected to pin number 12. So port or pin number is 12. And to configure that pin as a output, the argument is E underscore IO underscore output. Second one, INT underscore LED, initializing LED 1. For that also same function, but that port number is going to vary because LED 1 is connected to 13th pin of GPIO port C. And to initialize LED 2, the port number is 14th, and for LED 3, the port number is 15. This thing, that port number details, or the port number details are available in that schematic diagram. Next macro is LED 0 underscore on. LED 0 means it's connected to 12th pin. Okay, to turn on that LED. To turn on means we have to drive low signal to turn on the LED, because all are active low signals to control LED. So to turn on means active low. We have to drive low. Low means I'm using that function called drv gpio underscore clear bit. It has two arguments. One is that IO group and port number. LED 0 is connected to port 12, so that port or pin number is 12, and GPIO on that IO group is GPIO port C. So the argument is E underscore GPC. That IO group is going to be common because all these pins are from the group called GPIO port C. And to turn off the LED, macro name is LED 0 underscore off. Okay, to turn off that LED, so turn off means active high. Okay, we have to drive high at the pin number 12 of GPIO port C. So we have to use set bit function. Okay, again it has two arguments. One is that IO group is a port C, and port or pin number 12. And next macro is LED 1 underscore on. Okay, it's the same as that of that LED 0 underscore on. That only changes is the port number. Instead of 12, here it is 13, because 13 pin is connected to LED 1. And to turn off, we have to use that function called set bit, and again the two argument IO groups and port number is 13, and so on for LED 2 and 3. And for delay also, we define the macro called delay. Okay, if you want to change the delay, you can change this number. Okay, the function to create a delay is drv sys underscore delay. Okay, the macros are already defined here. Now come to the main program. This main code, first of all, we have to set the system clock to run at 48 MHz. We have to use a function to configure the system clock is drv sys underscore open. Okay, that argument we have to specify that value for 48 MHz. Value is 48 followed by 6 zeros. Here you can see unlock register function and lock register function. We have to use this function because of system control registers are write protected. So to disable the write protection, we have to use a function called unlock reg. after the modification, once the modification has done, okay, we have to enable the write function. To enable, we have to use that function called log or eg. Next statement is a user defined function called int underscore led. Here we have to initialize 4 led. First of all, we have to declare all the 4 leds output type, then followed by we have to turn off all the led 0 to led 3. To initialize, here is that user defined code. So here you have to only specify the macros, because macros are already defined here. Init led 0 means here is a macro, drv gpio underscore open e underscore gpc comma 12 comma e io underscore output. Macros are already defined, only we have to use macros. For 4 LEDs we have to write the macros to initialize 4 LEDs: init underscore led 0, init underscore led 1, init underscore led 2, and init underscore led 3. So we initialize the GPIO pins 12, 13, 14 and 15 to output mode. Then we have to turn off the LED by providing low signal at the pin number 12, 13, 14 and 15. So we have to use only that macros instead of using that set bit function, because already these macros are defined above. So now all LEDs are initialized. Next is a condition loop called while condition is 1. Okay, this condition is always true. This loop is going to execute forever. So first step, we are turning on the LED. Here also we are using macros. We are turning on the LED followed by delay, then we are turning off the LED, then delay. Okay, all the delays have the same time interval. Next we are turning on that LED 1 for a particular delay, then turning off. Again we have to wait for some delays. Again LED 2 on, LED 2 off, LED 3 on, LED 3 off. Okay, so this loop going to repeat forever. So when compared to the previous demo, if you're using macros, it is very easy to read, easy to understand the code. Okay, now we have to create an output file. Again, the procedure is same. We have to build this project by clicking build icon. See, there is no error and there is no warning, so we can directly load the program by clicking the load icon.
Now we will see the demo of interfacing 4 onboard LEDs to the GPIO pin of NUC140. The output files are loaded into on-chip flash memory of NUC140 devices. Now we have to execute the code by resetting the controller. You can see the output here. 4 LEDs blinking one by one.
Now we will see the demo of interfacing RGB LED to the GPIO pin of NuMicro 140. In this demo, we are going to interface RGB LED to the GPIO pins. So project name, again the 3 subfolder, CMSIS file folder, library files. Again it has only the 2 files, gpioc and drv6.c, source file to interface RGB LED. Here, before going into that source code, first of all we have to know which GPIO pins are connected to the RGB LED. GPA 12th pin is connected to blue LED. GPA 13th pin is connected to green LED. GPA 14th pin is connected to red terminal of that RGB LED. So to enable the LED, to turn on the LED, we have to provide low signal. We have to drive low signal. That means it's an active low type of interface. It's a device specific header file and peripheral specific header file we included. Next, come to that main code. Here we set the system clock frequency to run at 48 MHz using the function called drv sys underscore open. Okay, here you can see two function unlock reg. This function is to disable the write protection and to enable the write protection respectively. Okay, some of the system control registers are write protected, so if you want to modify that kind of control register, we need to have this kind of functions. Next statement is user defined function called init underscore LED. We'll go to that function. Here's declared. Again, initialization means we have to set the particular port particular pin IO type as a output, and we have to turn off that LED. Okay, so to set the output mode, we have to use the GPIO specific function called grv Gpio underscore open. It has three arguments. First one is IO group, second is port or pin number, third one is IO type. The previous two example, okay, we interfaced onboard red LED, okay, that is connected to GPIO port C, but this onboard RGB LED is connected to GPIO port A. Okay, so to enable the GPIO port A, we have to use the macro called, we have to use the argument called e underscore GPA, okay, to enable the GPIO port A. And next argument is a port or pin number, 12th pin. 12th pin is connected to blue LED. And next one is output type, IO type. So to configure the particular pin is a output, we have to use the argument called e underscore IO underscore output. Okay. To set the green LED, that is a port number 13. Okay, we have to use the same function, the same argument, only changes in the port number. Same thing for GPA 14 pin. Next is to turn off the LED. To turn off, we have to drive low at pin number 12, 13, 14 of GPIO port A. To drive low, we have to to drive high. We have to drive high to turn off the LEDs. To drive high, we have to use that GPIO specific function called grv GPIO underscore set bit. It has two arguments. One is the IO group and next one is a port or pin number. Here IO group is e underscore GPA. Okay, the argument to enable the GPIO port A, and followed by port or pin number 12, then 13, then 14. Okay, now initialization is done. Next is the infinite loop while of 1. First statement is a function called drv Gpio underscore clear bit. It has two argument. One is the IO group, and the second is the porter pin number. Okay, so if you drive low to the particular pin, it will turn on that LED. So 12 means now it will turn on that blue LED. Turn on that blue LED. And same time we are turning off the LED green and red. Then we are providing some delay. After that we are turning off by using that set bit, because if you are driving high at the pin number 12 means to turn off the blue LED. Next we are driving low to the pin number 13. This will glow the green LED. Okay, we are turning off that red LED, then followed by same delay. Here we are driving high to the both blue and green pin, and we are driving low to turn on that red LED. Then we are providing the delay. The last we are turning off all the LED by driving high, then delay. Again this loop will repeat. What it will do, first it will turn on green, sorry, it will turn on blue first, then green, then red, then it will turn off all the LED. Again it will turn on blue, green, red. It will continue at specified interval. Now we have to create an output file. To create an output file, click on build icon. There is no error and warning. You can see here in the build output window. So to load the output file into the target device, click on load icon. To load the output file into the flash memory of on-chip flash memory of target device.
Now we are going to see the demo of RGB LEDs. The output files are downloaded into on-chip flash memory of NUC140 devices. So to execute the code, we have to reset the controller. Now you can see the output red, green, and then followed by blue.
In this video demo, we saw how to interface LEDs and RGB LEDs to the GPIO pins of NuMicro NUC140 devices from Nuvoton. If you have any queries regarding this demo, please write to us at support@ala.co.in. You can also visit our website www.ala.co.in. You can follow us on Facebook social network www.fb.com/ala-technologies to know our training or workshop event, or on any update on our video training materials. Thanks for watching this demo.